subtracting, I have no idea.
25.
It's 25 because yesterday was 26.
What's 25? Days to oh, dude, it's 20 something. It's a number. It's a number. That's all we need to do.
All right. This, as I'm going to summarize here really quickly, this is the third of three very typical types of KSP problems you're going to solve. This ends up being what many people refer to as a 27x to the fourth problem.
Yeah.
You guys can see where that comes about. Yeah? Okay. Anytime you're going to have 4 ions, regardless of how you get there, it's going to turn out here. So anyway, we get A times 10 to the negative 19, and therefore, once you do all this little math work there, you get 9.3 times 10 to the negative 6. Whoa. Molar. And so there's the molar, which is equal to, as we were saying yesterday, the lanthanum concentration, which is equal to the lanthanum fluoride concentration. So that's why that's the molar solubility of the lanthanum fluoride. Is everyone good? Pretty solid, right? And about the only thing that probably was made as far as a mistake anywhere was maybe writing 27x to the third or possibly 9x to the fourth. I've seen people do that. Okay, but other than that, you're pretty good. So here's the the 3 main types of these that you're going to run into. We've already run into, I think that might be our third one. You're going to have x squared problems, you're going to have 4x cubed problems, and you're going to have 27x to the fourth problems. And it just determines, dependent on the number of ions that you're dealing with there. Okay. Moving on. Next. Now I think you guys on the next page just have one thing at the top, right?
Yes.
Well, unfortunately, I didn't get a chance to put, and I didn't want to waste another piece of paper. So there is a second example that's going to go on that page. We'll just write that problem out. I didn't want to make you guys tear that sheet off and add another one, so here we go. With this material, time out, I forgot. There's a couple bits of information at the bottom of page 10 I wanted to address. Because this is an equilibrium thing, the molar solubilities, the KSPs are an equilibrium thing. Just like we've been using equilibrium or K values to determine whether it's the reaction shifts way to the right, the equilibrium position lies way to the right or way to the left. We've been using that to evaluate how far the reaction proceeds. Okay. It's not as quick and clean with these KSPs as it is for the acids and bases because of the stoichiometry. So for example there, I gave you a couple of compounds, magnesium hydroxide, iron carbonate. We see that the magnesium hydroxide it does have a smaller KSP. Would you guys agree? Okay, based on what you're looking at there, which seems to imply that it's not going to shift to the right as far as the iron 2 carbonate. However, when you look at the molar solubilities, you'll see that the magnesium carbonate is more soluble than the iron 2 carbonate. And that has everything to do with the stoichiometry. So the KSPs are giving us an indication somewhat. It's getting us in the ballpark, but it doesn't explain everything, is what I'm trying to say there. Because the only way you can do that, the only way you can compare KSPs and solubilities is if you have substances that have the same number of ions. So if you look at the next set there, you'll see the magnesium hydroxide, 3 ions, calcium fluoride, 3 ions. Hey, they both have 3 ions. Now we can directly use their KSPs to make a comparison as to their solubility. Does that make any sense? Okay, so that's the only little thing. Honestly, I haven't seen that piece come up on an AP exam yet. That doesn't necessarily mean that it won't. It's a fairly easily figured out thing, so I just wanted to draw it to you. All right, next. Predicting whether something's going to precipitate or not. Up until this point, you guys have kind of memorized, in a way, the solubility guidelines. Is this going to precipitate or isn't it? Well, now that we know how to calculate solubilities and such, we can use these pieces of information to help us make these determinations. So, we're going to compare Q, you guys remember what Q is, initial concentrations versus K, the equilibrium concentrations. And I'm not going to sit here and have you guys, if Q is greater than K or K is less than Q. I'm not going to go through that because I don't want you to memorize, I want you to think things through. The example we're going to look at is taking some lead nitrate, mixing it with some sodium bromide to form, and so in solution, those will be 0.015 molar lead nitrate and 0.035 molar sodium bromide. So, let's go ahead and write up the equation here. Just for fun, well, I'll let you guys catch up. You guys go ahead, if you get done, go ahead and see if you can predict the products. It shouldn't be too difficult. Aaron, not an incredibly good idea to put this right next to my coffee pot. I know it has plastic wrap on it, but you've never drank my coffee, have you? It'll eat through most things, including those stuff. Yeah.
Strong, dark, and powerful enough to destroy planets.
Has anyone ever made coffee before?
Yeah.
Like not, I'm not talking a Keurig thing, that's not making coffee. I'm talking like a filter, put coffee in, okay. One of the days I was gone, I was actually not gone, I was over here having a meeting with other science department members. Mr. Crone was there. You guys know Mr. Crone?
Yes.
Okay. Anyway, so I took my coffee pot down there thinking, hey, most of us drink coffee, we don't have to go out and get anything, so we sat there. So I made coffee in the morning, and I think we just made the one pot, and I made mine kind of strong relative to most people's taste. So I even backed it down a little bit, and still was apparently a little strong. So anyway, it doesn't matter. So we go out to lunch, and come back, Mr. Crone decides that he would like to have some coffee. But as it turns out, the only thing he's ever used as a young person is a little Keurig kind of thing, right? And so he'd never actually made coffee before. Not that it's rocket science or anything, but still.
You don't know, you don't know.
Yeah, and so he had no idea how much coffee to put into the thing. He only wanted to make a little bit though, because he thought it was just going to be him drinking it. So when I make my coffee, I fill 10 cups, the 10-cup thing, and I put in a heaping scoopful. Okay, and I get strong coffee anyway, and I put in a heaping scoopful. He makes his coffee. Hey, if anybody wants a little coffee, I got a little left over. Oh, he goes, but this is the first time I ever made it, so I'm not really sure. Apparently, well, he only wanted 4 cups, and he put in 2. Yeah, that was strong.
Strong, dark, and powerful enough to destroy a planet.
Was that even strong for you?
Well, I drank it because,
Yeah, you don't want to make it too.
basically he made espresso times 2. So moving on. What are the products of this reaction? Oh, he didn't drink much of it.
Be lead bromide.
Lead bromide And sodium nitrate, I believe, yes? Now, which of these is going to precipitate? Has to be the PBBr. Two.
Okay.
Yes. And remember in balancing, there's going to be two of those. This stays in solution. Okay. And we're going to need two of these. All right. Here we go. Now, you might be asking, well, how am I supposed to know if this precipitates or not? Is that kind of going through your head right now?
Sure.
Okay, so we have to look at our products. Which of these two products form to precipitate? Obviously this one. So this is the one we have to decide whether it will precipitate or not based on the amounts of ion that are present. So we're going to have to look at a second reaction. Is this going to be soluble? Now we predict that it's going to precipitate. We know this isn't going to precipitate. We know that, okay? Will this? Now from our solubility rules, we've learned that, well, yeah, it will. However, that depends on how much of this is available, okay? Because it will dissolve to some extent. And I believe, did I give you a KSP for that?
No.
Okay. Here is the possible thing that might precipitate. And if it were to dissociate, it's going to dissociate into that and this. Okay? And so what you would have to be provided with in one way or the other, either embedded in the problem or given a table of these things, who knows, you'll need a possible KSP for that. As it turns out, it is 4.67 times 10 to the negative 6th. Based on some of the other KSPs we've looked at, what does that tell us? It's a little soluble. If I remember that, didn't we do the...
There's one like negative.
Oh, that's the one coming up. Yeah, one was like negative 19th. The other one was negative 10th. Okay, this one's somewhat soluble. So the question now becomes, is there enough of this material in there to dissolve or to continue to be soluble? And this is what we're going to find out. So we kind of do our little ice thing. As we know, this is not going to be included in it. Initially, when we first put that in, this is not going to change at all. These become x, and this becomes 2x. So at equilibrium, we get x, and we get 2x. So remembering that KSP, whoa, time out. We're using Q. We don't know if we're at equilibrium yet or not. So we're going to use Q. And the Q equation is going to be just like the KSP equation. Okay, and so now we're going to get x, and 2x squared equals 4.67 times 10 to the negative 6th. So eventually it becomes a 4x cubed problem, right? So x equals, or sorry about that, we're solving for q, my bad, I should have done that. I'm sorry, my bad. We're solving for q. Sorry about that. So we're actually going to plug in our values. So in that case, it's going to be what? What is my lead concentration? 0.015. Sorry about that. Ran into the thing that's not there. And what is my bromide concentration?
0.0035.
Yeah, it is 0.0030 or 0.00350. Except we're going to have to square that quantity.
We're also gonna have to double that.
Why?
You only have one bromide ion, or
Dang it, see, I was hoping we had fixed that. This was kind of a little test to see if we had fixed that. How much bromide is in there, in that solution?
Oh, only that much.
Only that much. See, this is, remember earlier, chapter 4, we ran into this problem? It
Yeah.
took us a little while to get over the hump of, you see, so the solution itself is 0.00350 molar in sodium bromide. The balancing doesn't have anything to do with it. Okay. That's all right. We needed to revisit that. That's okay. I'm going to throw a couple other things at us today also. They're going to revisit that. So anyway, we just come up with this value, and it turns out to be, we can kind of corroborate here, but I got, you know, here's my thing, my fault. This was my fault. We didn't need to do this. This here. That's my fault. I wasn't thinking of what I was doing.
I mean, it's
All I needed to do was say, this is 0.015 molar, and, oh, sorry about that. This is 0.015 molar, and this is 0.0035 molar. That's my fault. I just got carried away with doing it before we broke it.
I mean, it's basically.
No, it didn't matter. It's just that
It didn't have.
didn't have to do that. Okay? So now you just plug and chug, and I ended up getting 1.8 times 10 to the negative 7th. You guys concur? Okay, so that is the initial set of conditions that we have here. Okay? Will this precipitate? Well, this is Q. How can we compare Q and K? As it turns out, Q is less than K. Now, what does that mean? Well, remember, at equilibrium, we have a greater value, which means there is more of this stuff at equilibrium. Do I have that amount of stuff? I do not. So how would we interpret this? Is there going to be, are we going to see a precipitation or not? No, we are not going to see a precipitation.
Because Q is less than.
Because, yeah, I don't like to say that is true, because Q is less than K, we're not going to see it precipitate. It's because there just isn't enough in here to reach this point, in which case it would precipitate.
So there's not enough.
There's not enough to cause it to precipitate. So that material, the sodium, the quantities of the lead bromide that are lead ion and bromide ion that are available are enough to still remain in solution. Because we remember, we talked about the fact that we're thinking this is somewhat soluble anyway, compared to some of the other ones we've seen. As it turns out, this wasn't enough to cause it to precipitate. Yes?
So does Q have to be at least equal to the solid state?
Yes,
So it has to be at least K in order for
Yeah, because remember, cellulonic is we're dealing with a saturated solution. One in which, and remember, the way we're going to define a saturated solution is one in which there's a little bit of the solute, because it's an equilibrium thing, there's a little bit of the solute that has not dissolved, so that we can have an equilibrium process occurring. So in order for that to happen, it has to be some precipitate. Does that make any sense?
So Q must at least equal K for the.
Yes, and actually it should go beyond it. Because if Q equals K, that would kind of, yes, it has to be equal to it. Okay. All right. This kind of problem has shown up once in a while. They're asked, will a precipitate form? This is how you would find out. All right. Let's try this one more time. I'm not, I'm going to kind of say on your own, but not entirely on your own. We'll walk through it. Those of you that think you got it figured out, then obviously go right ahead and go. Here's the next problem. I want to see how I have this written up. Shoot. A solution is made. You just have to write this out. My bad. A solution is made from a mixture Up 50.0 milliliters of 0.00450 molar calcium nitrate and 75.0 milliliters of can't read the concentration. 0.00330 molar. What was it I used? Potassium carbonate. Will a precipitate form? All right, so what's the reaction? Yes. Oh, is that what you're gonna do? Oh, okay. So we got some calcium nitrate reacting with some potassium carbonate. By the way, for those of you that want to move on quickly, well, before we do that, what are my products? Potassium nitrate and calcium carbonate. Is there a chance for either of these to precipitate? The calcium carbonate has a chance. This is completely soluble. Boom. So the KSP for calcium carbonate is 4.96 times 10 to the negative 9th. Those of you that feel comfortable with what's going on, you can go ahead and jump in. Since it's the calcium carbonate that has a chance of precipitating, that's the equilibrium process that we have to consider ourselves or concern ourselves with. So let's look at that. What is the concentration of calcium ion that's available? Everyone concur? 0.00450 molar? Carson doesn't concur. A couple others of you are also thinking about not concurring, but you're not sure why. What's that? Yeah, the previous problem, notice how the two problems were constructed. The previous problem said, here is a mixture that is this in this material and this concentration in this material. So I already told you what the concentrations were within the solution. This one, this is a little bit more realistic. This would be like you guys in the lab. In fact, actually, that's where I took the problem from, is the lab that I did with my regular chemistry kids, the milkshake lab, where we used the vacuum filtration. We made calcium carbonate. Okay, that's where I got the idea for this question. Is those are exactly the quantities that we use. We use 50 milliliters of this and 75 milliliters of something else. We mixed the two things together. We did get a precipitate. You guys may remember that. That's the whole point of the lab. Okay, so
Would we multiply by the
come on, I'm waiting for somebody to help me figure out how to find the new concentration.
Where are you gonna need them?
M1V1. There we go. It's been a little while. I'm trying to bring everything back that I can possibly bring back. So I'll let you guys fiddle with that and come up with your new concentrations and let me know when you get them. I know that is true. I can't remember that. Now, my next part of the question is going to be how much is going to precipitate out. You want to dive in?
I got 3.6. They got 3.56, but that's good. What? That doesn't mean it's only racing.
I got 0.001.
Well, did you convert the milliliters to liters? And then you divide it. Where is it? You found the moles of each one first, and then you divided it by the 125. Oh wow.
Okay, oh, that's right. Thanks.
Okay, my bad, I got stuck. What do you guys get for a concentration of calcium ion? 0.02? And what did you get for the carbonate ion?
0.00.
Wait a minute, I gotta look. No, I got the 0.02 for the carbonate.
Yeah, I was just saying, definitely didn't get
Yeah,
that.
it's the same, basically.
I got 0.001.
I got 0.00.
Yeah, I got 1/8 for the calcium. They're not exactly essentially the same. The other one I got 0.00198.
Oh wait, no,
Yep.
I'm still wrong.
Yeah.
Never mind.
You guys hunky dory there so far?
Yes.
Okay, so now.
0.00.
No, it's 0.
Oh, my bad. Yep, you're right. Okay, so there's that. So that, honestly, so far, that was the hardest part of the problem. Would you agree?
Probably.
One, remembering, but once you remembered, okay, that's easy. And so now it just comes down to KSP, is equivalent to the calcium ion concentration times the carbonate ion concentration. It's 1 to 1, right? Okay, so, let's have a Q, my bad. And so that comes out to 0.00180 times 0.00198. And I got 3.60 times 10 to the negative 6th, which is greater than the KSP. Therefore, we've reached the limit, which I forget who it was that was asking that. Okay, we've reached the limit. In fact, we've gone well beyond the limit. You guys with me on that? So the conclusion here is a precipitate will form. On the AP exam, I have never seen them go beyond that. Will a precipitate form or not? What's your evidence? What's your reason? Okay? And sometimes they won't even, the only reason I threw this part into it is because it's been a while. And we need to start that process already of reviewing that material. I don't anticipate them ever doing that to you in a problem.
So we'll just give you the concentration.
So I've also seen them I've just seen them flat out give you these.
I'll just be like, analyze it.
And then just figure out what that means, okay? Yes.
I use different numbers, but got the same number.
Okay. No, you would get points off for your different numbers, but you would not get points off for your analysis of those different numbers. I understand that. What you would have done is gotten points off for not having the correct values, wherever that mistake was made, okay? But and this is what I'm saying again, you analyze your incorrect values correctly, so you would have gotten that. For example, what if you had got a different conclusion and that Q was less than A? If you said, no precipitation form, yeah, you would have gotten that. Those ones.
Pretty sure everyone's going to go through.
All right.
Your analysis was correct.
The next question. I'm sure some of you are thinking this. Okay, 2 of you are thinking this. What else could we figure out from this?
How much?
Were you thinking that? Awesome. How much is going to precipitate? How would we go about determining how much would precipitate? Yes.
Subtracting the KSP from the Q.
No. That's just the relationship between their equilibrium positions.
Isn't it just a rat going right again?
Once we know K, what can we calculate? Molar solubility. The amount of stuff that's actually going to dissolve, right? We can also calculate the molar solubility from the Q. Now, we're not going to go through both. Did you head in that direction or not? No, okay, okay. So let's go ahead, because it's going to be the same process for both. Let's calculate the molar solubility of the calcium carbonate from this. Now remember, molar solubilities are calculated using the Ks, which is 4.96 times 10 to the negative 9th equals the calcium ion concentration times the carbonate ion concentration, which ends up being x squared. Would you guys agree?
You'd use the second reaction step first.
We would have to use this, yeah.
That's
Is that what you meant?
Yeah, that's what the KSP is for.
Okay.
Yeah, that makes sense.
That will give us the molar solubility, because X will equal the it doesn't really matter which one, will equal both the concentration of the calcium ion or the carbonate ion, which is equivalent to the calcium carbonate concentration. So whatever the x ends up being.
7.04.
That's not what I got.
Oh, that's
Guys are on.
Anyone get a value for x yet? Say this again.
7 times 10 to the negative fifth.
Is that what you got?
yeah, square root of 4.96. That's not. Yeah, I'm getting 7.04.
Oh, you know what? I didn't finish the problem. My bad. I did over here. Time out. 7 times 10 to the negative fifth?
Yes.
Okay, that's what I got. I didn't do it on my paper. Okay, so I got 7. Now that's the molar solubility. Okay, moles per liter. All right, which would we would then have to do what? Compare to grams. That's 100.09 grams per mole. And then, so there's our grams
And then put it
per
over-
liter. Then what we would do is do the exact same thing for the value we got for Q, and we would just subtract. Does that make any sense?
Yeah.
Okay. Hey, listen,
Does Dad? I forgot.
have that assignment done for chapter 17. Yep,
We don't see you Monday. Well,
Tuesday. Next time I see you,